In this video, we're going to cover how to solve systems of equations by using the elimination method. Right from the beginning, we should note that the elimination method is just an alternate method to the substitution method that we use for solving these things algebraically. So if you're ever asked to solve a system of equations algebraically, we can either use the substitution method or the elimination method. The elimination method is also sometimes referred to as the addition method, depending on the textbook or the resource that you are looking at. So just noting that it does go by two names, but the process is very much the same regardless of which name you're using. Now we do have this principle here, the addition-subtraction principle of equality, that is allowing all of this to work. We do have the definition of this right here, and you're welcome to look that up online if you would like to. The exacts about it aren't entirely necessary to know for this process, but it is something that you can use as you are going through this, and something you can look up. Now, the process that I'm giving here, I want to give a couple warnings and just heads up regarding this. This is not the only method and not the only process that you can see and be presented with to actually use the elimination method. There's actually about 4 or 5 different variations to the elimination method that you can use, and a lot of them work, but I do find other methods have a lot of potential snags that can show up in them that I think are largely eliminated with using this particular method here. So if you look up a different method online, or you look this method up online, I should say, and they're doing it slightly differently, specifically in our second and third steps when we get to those, that's where the main change comes into play here. But just note that that method and that process works the same as this one. They will both get you to that final answer, but some warnings and hiccups that can show up with that, negative signs and all that here. So let's actually take a look at our method and our process with this. So first and foremost, we need to rewrite both equations into general form, which is also referred to as standard form. That's ax plus by equals c, where a, b, and c are all integers. The long and short of this is we want all the variable terms on one side and all of the constant terms on the other side. So start with that right from the beginning of the problem. Always a good place to begin these things. If you don't have it in standard form, this general form here, I think the rest of this process becomes way more sketchy, and there's a lot of potential room for error with that. The next thing that we're going to do, and this is one that's going to sound weird until we actually go through and see it live with an example problem. We are going to multiply one or both of the equations by a constant value, meaning every single term is going to multiply by something. So both of the equations have one variable with coefficients that are additive inverses, meaning I want the x's in both of my equations to have additive inverse coefficients. An additive inverse is defined as having a number value that is the same but opposite signs. So for instance, if I have the number -7, the additive inverse of that is +7. If I have +5, the additive inverse is -5. Now when we are doing this step and finding additive inverses for one of the variables, either variable can be selected. You can choose to eliminate the x's, you could choose to eliminate the y's. It does not matter which one you choose. There are some quote-unquote tricks that people choose to use, but I have not found any one that is an always guaranteed this one's better, this one's worse. I don't think it exists out there. Our third step is to then add the equations together vertically to eliminate the one variable that we chose, the one with the additive inverse coefficients. We're then going to solve for the remaining variable, meaning if I were to make the x's in my two equations have additive inverses, they will cancel out when I add vertically. I'll have some y variable equals some number on the other side, and then I will just solve for the remaining variable y in that example. Once we have that answer for one variable, we're going to substitute the value that we found from step 3, y equals a number, for instance, in for that respective variable into the original equations given, and we're going to solve for what's left over. So this could look something along this line. I'm going to eliminate x's, and I will first find a y value. I then plug y into one of my two equations, and I solve for x and find its value after that. As an option to this, if you would like to, when we get both our x and y values, our ordered pair final answer, we can plug that ordered pair into both original equations and see if we do have the correct answer to this if both sides of the equal sign are equal to one another. Now the main part that we will see differences in, and this is where other processes and other people might be showing it a little bit different to you, instead of finding additive inverses, what you could do is make the coefficients identical to one another and then subtract the equations vertically. My warning to you, if you do this, you are going to have sign changes showing up when you are subtracting, and that is where a lot of people make mistakes and errors along the way with this elimination method in these types of problems. I have two examples down here that we can and will be going through. I do also want to note that because we are working with systems of equations, all of our potential answers that we saw in the 5.1 and 5.2 material can show up here as well, meaning I can have infinite solutions showing up, and I can have parallel lines where I get just a number equals a completely different number showing up, which means I have no solution. That can show up in these problems. It can show up in any system of equation problem, regardless of the process and method that we use. So to that point, if you are finding that you're getting no solution with the elimination method, you should also be getting no solution with the substitution method and with the graphing method, all of that. So one method isn't going to reveal an answer that the other ones wouldn't. Maybe your preference is for one method over the other, but the answer is always going to be the same thing regardless of the method that you use. So let's take a look at these two examples and see this process in action. Looking at our first example, we've been given our system of equations that's listed here. I recommend to everyone, as you are going through these problems, label for yourself, here's equation 1, here's equation 2, something like that nearby. But our first equation is 3x equals 2y plus 5, and the second equation is 9x plus 4y equals negative 10. Now our first step in our process says that we need to rewrite both equations into general form. That's ax plus by equals c. I need all variables on one side of the equal sign. I need all constants on the opposite side of the equal sign. Now my first equation here is not in general form. My second equation is, so I need to rewrite equation 1. Let's go ahead and do that now. And now I have equation 1 in that general or standard form. I can now rewrite my system of equations, and I'd recommend giving yourself a little bit of space to do that. A lot of people like to try and cram all of the work into as small an area as they possibly can, and I would not recommend that route. A lot of people who do that tend to lose track of their work, and things go horribly wrong that way. So give yourself space if you need it between this set of work and the other work that you're doing. In fact, I'm actually going to put a line here just to separate a couple things out with that. Okay, now I have my new system of equations, or at least rewritten system of equations. Everything is in general form. Awesome. Now, I need to make the decision. Do I want to try and eliminate the x variables, or do I want to eliminate the y variables? At the end of the day, it does not matter which one you would like to eliminate. You simply need to pick one and then commit to that. So I am going to, in this case, elect to eliminate the y variables. The reason I am doing this is because I'm noticing one of my y variables has a positive coefficient, the other one already has a negative coefficient. So in terms of making these coefficients additive inverses, one is already positive and one is already negative. So some of that work is already done for me. Now I need to determine what do I want to multiply this whole equation by so that this coefficient here is the same as this coefficient here. Now I could, if I wanted to, multiply both of them by something and scale them both up. Maybe I could make it 8. I could multiply my first equation by positive 4, and this would end up giving me a negative 8 in front of y, and everything else would change too. And I could multiply my second equation by 2, and that would make a positive 8 right here, and everything else would scale up. I do also have the option of only multiplying one of these equations and scaling only one of them up. I'm going to use that here because if I multiply this first equation by 2, the coefficient for y will become negative 2. So I make a note of that. I recommend making a note off the side here. I'm going to multiply equation 1 by 2. Now we can think on what does this multiplication look like, kind of like the distributive property. It means that every single thing in here, this 3x, this minus 2, and this 5 are all going to have 2 quote-unquote distributing through to it. So my new first equation is going to be 6x minus 4y equals 10. I did not change my second equation at all, so I'm just going to bring it down exactly as it was, no changes at all. 9x plus 4y equals negative 10. Awesome. Now that my y values have additive inverses for their coefficients, that's my second step completed. I can now move on to step 3. I'm going to add the new equations together vertically. I recommend writing out somewhere nearby, hey, here's where I'm adding things together. I'm adding the first equation with the second equation. What are my results going to be? Well, the variables that have additive inverses, these will cancel. Negative 4 plus 4 gives me 0. 0 times y, it's just going to be 0. So this whole thing right here is gone altogether. What's going to happen with my x's? 6 plus 9, that's going to give me 15x. I'm going to bring down the equal sign just like it was. And then 10 minus 10, I don't need to change any signs here, or 10 plus negative 10, you can think of it that way also. Those combine and those are going to be 0. Now there's nothing wrong with having 0 show up in these problems. It's actually a fairly common occurrence at some point in time as we go through these. But I'm just going to continue solving this thing for x. So I'm going to divide both sides by 15. And I'm getting that x is equal to 0. So there I have half of my answer determined already. So that's steps 1 through 3 just to get to my first half of the answer. I'm going to go ahead and divide this up here as we finish this problem off. Step 4 states that we need to substitute the value found in step 3, this 0 here, in for that respective variable in one of the original equations that was given to me. So I need to plug 0 in for x into the first equation or the second equation. It truly does not matter which one I use. I just need to pick one and then commit to it. I'm going to choose to use the why not? Let's use the second equation because my mouse was hovering over it. That's the level of specificity and kind of requirements to pick one over the other that we can use. Really isn't one that needs to be picked over the other. So I'm plugging 0 in for x, and now I'm just going to solve this thing for y. And now I have my y value, I have my x value. I can write this whole thing out as a single ordered pair answer. Then I have 0, comma, negative 5 over 2. If you are in my class and you are watching this, make sure that you do write your final answer out as an ordered pair like we have here, x value in front, y value second. If you are not in my class, you're using a different online program, just make sure you're keeping track of which variable corresponds with which number, and make sure you're entering that into the proper place on whatever program or site or person that you are working with there. But otherwise, this is our process illustrated with example 1. Our second example is a system of equations that is way grosser looking than our first one. I want to show you how we can go through this because we do have some tricks up our sleeve. So we're working with the first equation, that is x over 6 plus y over 9 equals 2. And our second equation is x over 8 minus y over 3 equals 9. Now, the left half of these equations are both very gross. We don't like the fractions in there. I don't think it's easy to find additive inverses with those fractions. So we are going to, within the first step of our process, where we're told to rewrite both equations in general form, as part of that, we are going to eliminate all fractions in each respective equation. Now, the way we do this is like we eliminated fractions in our, I believe it was the 2.5 section. I am going to determine what is the lowest common denominator between all fractions in this first equation. I am then going to also determine what's the lowest common denominator between all fractions in the second equation. And I'm going to multiply each equation by that lowest common denominator. So the intention with this is not to create additive inverses, but it is simply to eliminate fractions in these problems. So with my first one, I'm going to multiply both, or everything, I should say, both sides and everything, by 18. That's the lowest common denominator between 6 and 9. I'm going to multiply the second equation by 24. So I'm going to have some larger numbers showing up in here, but I am going to have fractions eliminated. You could think of this as the numbers here, 24 and 18 respectively, distributing through to everything inside of each equation, and then the fractions eventually eliminating down. I would recommend that you reference the 2.5 notes on how we go through and do that. This is coming directly from those, and I'm going to go ahead and work those out now and get us to our results for our next part of the equation. And now, from here, I notice that all of my fractions are gone. This is a much nicer system of equations to work with, and it's much easier for us to do our second, third, fourth, and fifth steps from here. So looking at our second step, we're told to multiply one or both equations by a constant, so we get additive inverses for one of these variable coefficients. One's a positive and one's a negative. Now, in the last example, I eliminated the y values, or the y variables, I should say, because they had alternate signs here. One's a positive, one's a negative. I don't need to deal with sign changes by changing these numbers, and you are more than welcome to do that here. For the sake of showing a different route that you could take, I'm going to instead eliminate the x variables. I'm noticing that the numbers are the same, which is half of the additive inverse, but I need to make sure that the signs are opposite of one another. So I need to make one of these negative. I'm going to arbitrarily choose to multiply we'll go with the first equation, why not? I'm going to multiply the first equation by -1. And again, the intention behind this is to create additive inverses for my x variables. We'll go ahead and write the result right down here. So now that I have additive inverses for my x variables, I can go ahead and move on to my third step, where I'm adding the equations together vertically. And again, I recommend that you write it out for yourself, make it clear that I'm adding these equations together, and then we can go through and actually do that. So with the additive inverses, negative 3x and positive 3x, those are going to cancel out. They will become 0x, which is just nothing. It's gone altogether. Negative 2y plus negative 8y, or effectively negative 2y minus 8y, is going to give me negative 10y. And then I have negative 36 plus 216. That's going to give me 180. Used a calculator off screen for that one, kind of a big number to calculate there, and you're welcome to do that as well. Now I'm dividing both sides by negative 10. I'm solving for this equation, for the variable that's left over in this equation, and I'm getting negative 18. So we've just completed steps 1 through 3 up to here. Now we're almost done. Let's go ahead and move on to step 4. We're substituting the value from step 3, this negative 18, in for one of the variables, or for that respective variable, y, in one of the original equations. Doesn't matter which one, we just got to pick one and commit to it. So let's see, do I want to divide negative 18 by 9 or by 3? It's kind of a toss-up here on which one's going to be quote-unquote better. I guess I'm going to choose the first equation because why not? I used the second equation, I think, on the first example. Let's do it with the first one here. So I'm just rewriting this. I'm substituting negative 18 in for y. And now I'm simplifying this thing, and I'm going to solve for x. We'll show that right here. And here we have our x value of 24. We can rewrite this. We take one last step and write everything together as a single ordered pair. We can go ahead and highlight this thing, and there we go. We have our final answer for example 2. A final note and warning that I do want to give you regarding the elimination method and the alternative way that some people like to go through and solve this is if we were to find and make the coefficients the exact same. The alternate methods that a lot of people like to use require us to, instead of finding additive inverses for these variables, what they will say is find and make the variables, the coefficients, the exact same, and then subtract the equations together. Now there's nothing wrong with this, but I do want to show and highlight how easy it is for an error to show up with this, and it screws up a lot of people when they're going through these problems. So, we followed the exact same process we did with our second example. We notice that, hey, the x's have the exact same coefficients in front of them. Great, I'm going to use the kind of alternate or a different method with the elimination method, I should say, different process with the elimination method. And instead, I'm going to go ahead and I'm just going to subtract these two equations together. So I write in subtraction sign here, and I go through my subtraction process. Now 3 minus 3x, that's going to cancel out, and that will just give me 0 altogether. And now I'm looking at this 2 minus 8. That's going to give me a minus 6y. And then I have 36 plus 216. Let me add those together, and that's going to give me 252. And then I go through and I would divide both sides by negative 6. And what do I get as my final answer? I'm doing the calculation off screen here. There we go. And I'm getting y is equal to negative 42. Now, if you followed that and you said, that looks great, that looks fantastic, this is how easy it is to make this mistake. Notice how the correct answer is up here, and look how different our answer is from what the correct answer is here. So here's the error that shows up, and it all has to do with this little subtraction sign here. This subtraction sign would go through, I'm actually going to cross off this or get the red line out of here. There we go. So what actually happens with this, to do this properly, is that this negative sign distributes through to everything in the second equation. So this 3x is actually a negative 3x. The minus 8y becomes plus 8y, and the 216 would actually be a negative 216 here, and then you can combine these things together vertically. But hopefully you're seeing how quick and easy it is to say, oh yeah, I'm just going to subtract this front thing and then forget about adjusting the signs of everything else in this problem. This is why I highly recommend we take the one extra step and find additive inverses for coefficients, so not only the values are the same, but the sign changes already happen a step or two earlier, and we don't need to worry about distributing a negative through in the addition or subtraction process with these two equations. I tend to find that that's the most common thing that gives people headache with the elimination method, and it all depends on if you find the same coefficients between variables and therefore subtract, or find additive inverse coefficients between variables and then add them together. Spoiler, if you find additive inverses, you will never need to make sign changes in this step and never have to worry about this. So, I'm biased, but there's the reason that I would give for using my method over using, I wouldn't say mine, but this method over finding the same coefficients. As a quick recap of the stuff that we covered in this video, we worked with the elimination method, just as an alternate algebraic method to solve systems of equations. This is also very commonly referred to as the addition method, so be on the lookout for that slight name change that shows up, depending on the book or the YouTube video or something that you're looking at there. Now we have our process listed out here. I highly recommend that you have this written down for yourself, and as you are going through this process, please, please, please reference this step-by-step guide for yourself and the examples that we went through. Tons of people do not reference this for themselves, and they subsequently keep the problems very, very difficult and keep guessing at what they should do next. This is here for you to write down and reference later, so please make sure that you actually do reference it later as you're going through these. We then had our two examples, the really gross examples showing up here, how do we deal with fractions in these problems. But we had our two examples and the warning that goes along with finding the additive inverses for coefficients or finding the same number for the coefficients. If you're looking for some extra practice, I do have 4 problems here. I'd recommend pausing the video right now and then working through these on your own, because we'll scroll down and we'll give you the answers to these. Hopefully you got the same things here. I did throw in a no solutions one, because again, this is eligible to be showing up with all systems of equations problems. But that is everything for our elimination method and subsequently all of the algebraic methods that we are learning for solving systems of equations.